Welcome to this interim lecture on polynomials over fields. In this lecture, we'll be looking at the unique factorization theorem for polynomials. I'll be a little bit sketchy and brief because this is entirely parallel to the analogous discussion in the context of elementary number theory. So let me recall a few facts from elementary number theory that run parallel to the discussion. So suppose we have a prime number and we have two integers such that the prime number divides the product of the two integers. Then it follows that the prime number either divides the first one or divides the second one or both. And so all of this is discussed in detail on my channel with a lecture series titled, starting with this under this rubric, Number Theory Primers. As of now, they are available in this playlist titled Kickstart. I hope I won't change the name or anything. So you can find that playlist on the homepage of my channel and see all those videos. It's about a dozen videos and very short ones. All of the basic number theory that one needs to get started is discussed there. The fundamental theorem of arithmetic can also be found there. It just says that if you have a natural number, then there is essentially a unique way to write it as a product of primes. And that is basically the analogy, or rather basically the counterpart of the unique factorization theorem for polynomials that we are going to discuss. All right, and just remember the Euclid's theorem for polynomials. So if we have two relatively prime polynomials, then you can find, two suitable polynomials such that if you product respective ones and take the summation, then the summation is 1. Yeah, so I don't want to write it down. We have done this so many times. All right, so let me define the main concept. Start with the field f, a non-constant polynomial, meaning a polynomial of degree at least 1. Let's call it px over f is said to be irreducible if whenever px equals ax times bx for some. So wait a second. When I say irreducible, I should mention over which field. Irreducible over f. Over f. You'll see why do I need to prescribe this additional thing. Irreducible over f if whenever px equals ax times bx for some ax and bx in fx, we have either ax is constant or bx is constant. Basically, you can't write px as a product of two simpler things, right? Essentially, the complexity of px here is preserved either in ax or in bx. So if ax is constant, then in a sense, bx is everything that px is. You're multiplying by some scalar, that's all, or the other way around. So that's a natural notion for a polynomial, and let's see some examples. So first, a non-example. So consider this polynomial over the field of real numbers. Then this is not irreducible because you can write this as a product of x plus 1 with x plus 1. And neither of these are constant polynomials. So that's that. But what about this? This is an irreducible polynomial over R. So is irreducible over R because if it were reducible, then you could write it as a product of two smaller degree polynomials, both of which are over R, which would mean that both these polynomials have degree 1. So if you can write this as a product of 2 degree 1 polynomials, that in particular means that this has a root in R. But this does not have a root in R, clearly. This is always positive, so this does not have a root in R. And that's it. So you cannot split over R. Split this over R as a product of two simpler polynomials. However, the same polynomial is not irreducible over C. Is not irreducible over the field of complex numbers because clearly x squared plus 1 equals x plus I times x minus I. I is the the iota, the 0, 1, or I don't know how to say it. It's e to the 2 pi, e to the I pi by 4, or e to the I pi by 2. Whatever, so again, but to define I, I'm using I, so let's not do it. You know what is I. It's the root of this polynomial. Okay. So that's why we need to prescribe. When we say something is irreducible, we need to say over which field, because the field that you start with may be sitting inside some bigger field, like R is sitting inside C. So one has to prescribe over which field are we talking the irreducibility of a given thing. All right. So let's move on. So here's a simple observation. Suppose we have a polynomial px, which is irreducible over f. So again, I should say irreducible over f. And suppose ax is a polynomial over f, such that px does not divide ax. Right? So then, when we say px does not divide ax, we of course mean that there is no polynomial bx over f, such that px bx is ax. So then, the irreducibility of px implies that ax and px are relatively prime. And this is trivial, because if they were not relatively prime, there would be a non-constant common factor between them. But then in particular, it would, that non-constant polynomial should be equal to px itself because of the irreducibility of px. And hence it would follow that px divides ax. That would be a contradiction. So that's it. I mean, just if it is not clear, you should just stay on it for a little while and you'll get it. Just a matter of definitions. All right. So this implies a fact about polynomials. So start with an irreducible polynomial over f. And suppose we have two polynomials over f such that px divides the product of these two polynomials. Then the conclusion is that it divides at least one of them. And this kind of thing we recalled in the beginning. It was a fact about natural numbers and primes. And the analogous fact is about irreducible polynomials. So this is just like the proof in elementary number theory. Suppose px does not divide, this is the symbol for does not divide. Px does not divide ax, then we want to show that px divides bx. Right? That's what the proposition wants us to do. So by the observation that we just made, this means that px and ax are relatively prime. And thus by Euclid's theorem, we have there exist polynomials. What should I use? Maybe ux and vx over f, such that px ux plus ax vx equals 1. Multiply both sides by bx, so we get px ux bx plus ax bx vx equals bx. Just multiplied both sides by bx. So this is of course divisible by px. There's a px sitting right in front. This is also divisible by px by hypothesis, and therefore the left hand side is divisible by px, and hence the right hand side, and that's what we wanted to show. So that's it. I'm not writing those steps. All right, so we have that fact, and now we can state and prove the unique factorization theorem. So start with a non-constant polynomial. I shouldn't have used px. Let me use fx. I'll change the notation. So start with any non-constant polynomial. Then we want to show that there exists a scalar and a bunch of polynomials such that each pi is a monic irreducible polynomial. So a monic polynomial is a polynomial whose leading term is 1, right? Such that px is a product of all these monic irreducibles along with a scalar. So basically the leading term of px is alpha, and that is what is appearing here. So you can split any given polynomial as a product of irreducibles and one scalar. At the same time, this decomposition is unique. So if you have some difference, some other scalar possibly, and some other list of irreducible polynomials, such that again you can write, so this is not px, I'm sorry about that, this is fx, this is also fx. Yeah, so if you can write fx again as a product of a scalar and some monic irreducibles, then first of all, the number of monic irreducibles that you see in the two decompositions is the same. The scalars are also the same. And in fact, the list of irreducibles that you see here is the same. So this list, P1 up to PR, is same as that list, Q1 up to QR, up to reordering. So up to reordering. So of course, if you can write fx as a product of, in this fashion, you can shuffle the positions of pi's. And that's essentially all that you can do if you want to write it in a different way. So it is only superficially different. Essentially, there is only one way to decompose a given polynomial as a product of monic irreducibles and a scalar. Alright, so I won't be proving this because the proof runs entirely parallel to the corresponding theorem, to the proof of the corresponding theorem in elementary number theory, which is to say that any natural number splits as a product of primes in an essentially unique way. The notion of primes is replaced by the notion of irreducible polynomials. And you have a little bit of a fudge here, which is the scalar. But there is no technical difficulty that you will face when you mimic that proof here. In fact, you don't even need to look at that proof. This is kind of obvious from what we have done. At any rate, so this is the unique factorization theorem. It's a very useful theorem. And let me just end it at that. So just note that this notation is fx. I initially wrote it as px, and here the same px came about, but it's actually fx. Okay, so thank you for listening, and I'll see you next time.